For each of the scenarios described below, indicate the amount of kinetic energy and gravitational potential energy of the object at each of the events listed. Use a consistent scale throughout both motions. Set ground level as the 0 point of gravitational potential energy. In part A, a baseball is thrown at 30 meters per second at an angle of 30 degrees above horizontal over level ground. We are going to look at when the ball first leaves the thrower's hand, that's here, when the ball reaches its maximum height, here, and when the ball hits the ground. In part B, the baseball is thrown at 30 meters per second, so same speed, but an angle of 60 degrees, so a different angle. Because we are in Model 2, when the ball reaches its maximum height, the velocity is not 0. So back in Model 1, when the ball went up in the air and then came back down at the maximum height, the velocity was 0. But here in 2 dimensions, the vertical component of the velocity is 0 when the ball is at its maximum height, but we still have a horizontal component for the velocity, which means we still have some kinetic energy when the ball is at its maximum height. So first of all, when we do the three sets of bar graphs here, let's pretend that when the ball leaves the thrower's hand, that's really at ground level. So if the height of the ball is really large compared to the distance between the thrower's hand and the ground, then that is a valid approximation to make. Or you could just pretend the thrower is bending over and releasing the ball from ground level. So if we do that, then I can say when the ball first leaves the thrower's hand, the gravitational potential energy is 0. If you don't make that approximation, then you'd have a little bit of gravitational potential energy when the ball leaves the thrower's hand. We're not going to be too concerned about the scale here, so I want to be able to do the bar graphs without pulling out my calculator. So I'm going to make the relationships as accurate as I can without actually doing any calculations. Okay, when the ball hits the ground, the gravitational potential energy is 0. When the ball first leaves the thrower's hand, I have some kinetic energy. I'm given the speed of the ball, and remember, kinetic energy is equal to 1/2 times the mass times the velocity squared. I'm not going to do any calculations, but I know that the kinetic energy is determined by the speed and the mass of the ball. And I'm just going to say initially I have 4 blocks of kinetic energy. You can choose whatever you want, but once you make that choice, you want to be consistent with the number of blocks that you have for each pair of bar graphs. So next, when the ball reaches its maximum height, it has some gravitational potential energy and some kinetic energy. I have to decide how much of that is gravitational potential energy and how much is kinetic energy. But remember from our work-energy relationship back in Model 1, and this is the same in Model 2, we have KE1 plus GE1 plus work 1, 2 done by forces other than gravity is equal to KE2 plus GE2. Once the ball leaves the thrower's hand, what forces do you have acting on the ball? Nothing is touching the ball other than air, which we are going to ignore. And so the only force that we have acting on the object is the force of gravity, which means work 1, 2 other is equal to 0, which means KE1 plus GE1 is equal to KE2 plus GE2. So let's say KE1 plus GE1 is equal to KE2 plus GE2 because we have no forces other than gravity acting on the object. Which means if I have 4 blocks total at event 1, I should have 4 blocks total at event 2. The closer this angle is to 90 degrees, the more like a Model 1 problem, this is going to be where the ball just goes straight up and comes straight back down. So if the angle was 90 degrees, then at the max height, the velocity is equal to 0. I'm not going to do calculations for this to figure out how much is kinetic and how much is gravitational potential energy, but I know if I threw it at 90 degrees, it would be all gravitational potential energy because the velocity of the ball at this point is 0. So I'm going to say the ball has gravitational potential energy here, and this is the maximum amount of gravitational potential energy throughout the whole time it's in the air. It still has kinetic energy. And you could actually figure out how much is kinetic and how much is gravitational potential energy. And I think what I chose here, where I have 3 blocks here and 1 block here, is correct. But we're just going to go with that and not worry about exactly how much is gravitational and how much is kinetic. But I do need 4 blocks because I started with 4 blocks. Okay? And then when the ball hits the ground, still between event 2 and event 3, the only force that we have is the force of gravity. So I should still have 3 blocks when the ball hits the ground. I should still have 4 blocks when the ball hits the ground. So all of that is kinetic energy, and that's assuming that I didn't have any gravitational potential energy to begin with. Now we're going to look at what would happen if the angle is 60 degrees. So when the ball leaves the thrower's hand, the speed is still 30 meters per second. So if I said 4 blocks for kinetic energy up here, I should keep 4 blocks because the kinetic energy depends on the mass, which has not changed, and the initial velocity, which is still 30 meters per second. So I'm going to keep this as 4 blocks. We're going to assume, again, gravitational potential energy is 0, so assuming that when the ball leaves the thrower's hand, that's actually at ground level. When the ball hits the ground, the bar graphs look the same as they did for part A. So when the ball hits the ground, gravitational potential energy is 0, and I still need 4 blocks total, so I have 4 blocks of kinetic energy. So the question then is, how does event 2 look when the angle is 60 degrees? So the ball started off with a speed of 30 meters per second, and there are no forces acting in the horizontal direction, so the horizontal velocity stays the same the whole time. I can take the initial velocity, which is 30 meters per second, and break it down into components using the angle, so that would be 30 degrees. So for part A, the velocity in the x direction is 30 meters per second times cosine of 30 degrees. For part B, now you have the same magnitude but a different angle. So this is 30 meters per second, and this angle is 60 degrees, and the x is 30 meters per second times sine of 60 degrees. 30 meters per second times cosine of 30 degrees is larger than 30 meters per second times sine of 60 degrees. So the x component of the velocity was larger in part A. The velocity in the horizontal direction stays the same the whole time. When you're at the maximum height, the velocity in the y direction is 0. So at the maximum height here, the speed of the ball is 30 meters per second times cosine of 30 degrees. At the maximum height here, the speed is 30 meters per second times sine of 60 degrees, which is smaller than what we had in part A, so I should have less kinetic energy in part B than I had in part A. So let's make this 1 block for kinetic energy, which means that I still need to have 4 blocks total. So if kinetic energy is 1 block, gravitational potential energy is 3 blocks, which means the speed is less for part B, but gravitational potential energy is equal to m times g times h. So the speed is smaller, but the height is greater. So it has a smaller speed at the maximum height, but it goes higher if you throw it at 60 degrees versus 30 degrees.